Hi everyone. We're going to work on functions finally. So this will require us to use all of our algebra skills, but just shift our thinking a little bit. So it's really just a new notation. We're learning symbolic language, and this is just a new level of that we need to work on. So don't let it be too off-putting. It really is just new notation and some new thinking, but not entirely new thinking. Not as new as some people like to imagine that it is. So basically, we have been, in our review, we were looking at relations between two variables, right? So for our expressions and our equations, mostly we were working with just one variable, not exclusively, but mostly. And in 4.1, I hope that we got reminded that you can write an equation in two variables, and it tells you the relationship between those two variables. So often it's x and y, but that's not required. So when I write down y equals 2x plus 7, that is a relationship that defines a relationship between x and y. Relationships don't have to be defined by an equation. They can be words, tables, graphs, all sorts of things. And we are going to study all of those types of representations of functions. So let me think if I'm missing anything in this first paragraph. Yeah, no, I think we're okay with that. So function, we're just going to narrow this down a little bit. Instead of saying we're interested in any relationship between two variables, it could be more, but we're looking at two right now. We want to narrow that down and only look at relationships that are functions. So there's a rule for what makes a relationship a function. And it's fairly simple, but it's easy to get directions mixed up a little bit in which way this implication goes. So the definition we have is a function relates every input to exactly one output. So there's kind of a couple of things going on there. One is that when we look at y equals 2x plus 7, we aren't necessarily thinking there's an input and an output there. There's just an x and a y, and we can find a y value given an x value or find an x value given a y value, and no big deal, no big direction there. So the first thing we're going to do is kind of imply a direction. We are going to build a formula or a table or a graph that's meant to say, if you give me the input, I will give you the output. So there is kind of a direction. That doesn't mean we can't reverse that. It's just a way of thinking about it. If I have a function, I'm going to input a number. It could be words or other things, but usually we're going to input a number or an expression, and we're going to output a number or an expression. The other thing there is the exactly one part. That's really the key piece in defining, does it pass the function rule or not? So if I plug in an input, I don't want the answer to be ambiguous. I either want it to give me one answer, or I want to say that wasn't something I should have plugged in the first place. So particularly a function should never give you more than one output. Let's see if I can think of some silly examples. Okay, so let's say we'll do a words one. Let's say we build a function and we're going to call it f. And this is the nice thing with the notation I'm about to introduce, is it just lets us name what the thing we're doing is. So my function is named f, and it inputs a social security number and it outputs a name. So the question, is it a function or is it just a relation, says if I plug in a social security number, should I expect to get exactly one name back? And the answer is hopefully yes, that is the plan. Social security numbers are unique, so there shouldn't be more than one person with the same social security number. So notice there's a direction on my arrow. This isn't a back and forth. I pick a social security number, I get one name back. People get a little worried because if you pick a name, multiple people have the same name, so it might trace back to more than one social security number. That is not a problem. So that's the directional confusion that's possible. It's only input to one output. If you start with an output, it could have more than one input that gets to it. That's okay. So it's only starting from an input going to an output. So another example would be, what if we did birth date? we have a function, I'm going to call it G, that inputs a day of the year and thinks about that as a birth date, and it outputs the names of people who have that birth date. So this one is definitely not a function. If I put in the day March 3rd, and I could even give it a year, March 3rd, 1995. I'm not going to get a single name. There were gobs of people with that birth date, so I'm going to get more than one output. So this is not a function, and this is a function. That's not to say that the birth date to name is no good. It's perfectly good. It's just not a function. Okay, let me think what else. Order here. Notation. I don't think I'm quite ready for notation. I think I want to talk about this is how exactly one output would work with words. We can also do this looking at graphs is kind of a particular interesting one. So let's say this is the graph of my function. These are my x's and these are my y's, and it just dead ends at those dots. So if I ask myself the question, is this a function? I would like to say that for any input, I get exactly one output. And what you want to know about graphs is that whatever's on the horizontal axis is your input. So we input x's and we output y's. So if I want to pick a single input, say x equals 1 is the input I'm interested in, x equals 1, this is where one-dimensional versus two-dimensional visualization is good. When we drew a number line, x equals 1 would just be that dot, but we're in 2 dimensions. So remember, x equals 1 is like this vertical line. And anywhere we run into the graph, we get a point on the graph, and that's pairing an input with an output. So for one specific input, we can draw a vertical line. Everywhere it hits the graph is an output, which means we would not want it to hit the graph more than one time. So what you want to visualize for graphs, this is called a vertical line test. If you move this line around, as long as it only hits the graph once, it's a function. If it ever fails to hit the graph, what do I want to say? If it fails to hit the graph, that just means you shouldn't have used that as an input, but if it ever hits the graph more than once, you're in trouble. So for example, circles are a fantastic relation between x and y, but they're definitely not functions. Anywhere I draw a line, just about anywhere, right at the end, I can draw a vertical line that only hits once, but everywhere else in the middle, it's going to hit the circle twice. That doesn't mean it's not a valid relationship. It's a great shape, it's a great graph, but it's not a function. So if you're looking at graphs of functions, vertical line test will tell you if it's a function or not. Graphs of relations, sorry. Okay, so the notation, this is a big part of what's new here. Hopefully you've looked at some graphs before, you've read descriptions of relations, but the notation I think is probably going to be new for a fair number of us. So the notation looks like y equals f of x. So for example, that y equals 2x plus 7 that I wrote down at the top, if we were using function notation, we'd say f of x equals 2x plus 7. And that again is just naming the relation. So f is the function that inputs an x, multiplies it by 2, and then adds 7. So whatever you input, it's going to multiply by 2 and add 7. And we have named that set of steps f. We could similarly, and you don't have to name it f, f is nice because it's function, but whatever you want, we could say m of t is 3 minus t squared, and then I would say m is the name of the function who squares your input and then subtracts it from 3. So notice we're back to order of operations. It's a big theme for us. So I've named the steps that make up this function m. Okay, so in my more general thing, y equals f of x is how I would read off this first part. And what it tells me is that y is the output you get from function f if you input x. So when I'm looking here, m of t is the same as y. So whenever you see f of x or m of t or g of x or whatever it is, that is your y. So here, m of t is the output that I would get if I plugged in a t value. And you could write down specific statements. We'll work on actually doing the work for this later. But if I said, for example, g of 2 is -3, that means there's some function g, and I don't know what its steps are, but it's out there, it's named, that takes the input 2 and returns an output of -3. And remember, if we're thinking about points on graphs, 2 is the input, those would be our x values, -3 is the output, those would be our y values. So we could also say that the graph of g goes through the point 2, -3. Okay, so we're going to do tons and tons of practice, but basic things I want you to get here is that a graph relates to, a two-dimensional graph relates to variables. An equation with two variables is a relationship between those variables. We could have tables with x and y values. And that's a relationship, that's telling us about a relationship with two variables. What we're doing in this section is defining a type of relation where you have an input-output sort of direction going. You know what's input, what's output, and you know that if you plug in one input, you'll get exactly one output. So that's what we're going to study for like the rest of this class, all of pre-calc 1 and 2, functions. Functions are a big deal. So we are, like I said, just a little shift, doing just a little shift in our thinking. It's actually not as dramatic as it might seem at first. In this intro stuff, I think I also want to just bring up a little bit of the vocab, and then I'll jump into specific examples. I just want a video with all this in one place. So with a function, we have specific variable for our inputs, variable for our outputs. And it's really important that we can talk about what are possible inputs and what are possible outputs. And so we give those special names, and they're, I don't know, for me at least, unfortunate, because just seeing the names on paper doesn't make me link them to what they are. But the domain of the function is all possible inputs, and the range of a function is all possible outputs. So if we're looking at a graph, remember inputs go on the x-axis, outputs go on the y-axis. So all the x values that the graph takes on would be your domain, and all the y values that the graph takes on would be your range. So that's just a straight up memorize thing. Remember which one is inputs and which one is outputs. That's absolutely something I'll be testing you on, so you just want to make sure you remember which word is which. I think kind of last new thing, we've already talked about rate of change. We just need to introduce it in function notation. So last new thing is just to make sure that we get a little bit of dependence stuff. We'll need that, I think, in the next section. Dependence, when we're back to graphs again, when we're graphing, if we have a function, y is a function of x, and we have our x-axis, our y-axis, and we have our graph that relates the two. Dependence is kind of like input-output. So if we were doing this, we would say always y is the dependent variable and x is the independent variable. And if you think about functions, it's sort of that input-output thing. X is independent of y. You pick any x value you want. The function is built to take that x value and run it through whatever rule the function follows, whatever steps the function has, and output a y value. So the y value will depend on your x value. So sometimes people, like in the linear function section we're going to do next, have a hard time deciding which should be their input and output. So remember, you can use that dependence word. Y depends on x. So if you have a function that relates height to age, does it make more sense to say a person's age depends on their height or their height depends on their age? And sometimes it's a wash. Generally, I would say height depends on age is probably the way we would think about it. But sometimes it can go either direction. But that's one thing to keep track of. Dependence and function notation kind of tie in nicely together. Okay, last thing in your background video, your background knowledge, is average rate of change, which we did before, but now we can make it a little more formal. Before we said the average rate of change in something is like a slope, right? Change in one thing divided by change in another thing. So if we're talking about the average rate of change of a function, it's going to be the change from one x value to a next, And basically its slope, this might not scream slope to you right away, but I hope it will eventually. Remember I said f of something is always a y value? So this is like the y value that goes with x equals b, and this is the y value that goes with x equals a. So on the top, I'm subtracting y values, and you could even do something like y2 minus y1. And on the bottom, I'm subtracting x values. So this is the average change in y over change in x. So the reason it has a fancy name is because not all functions are straight lines. And slope specifically means the constant rate of change. The definition of what makes something a line is that it has a constant rate of change. Y always increases at the same rate with respect to x. So if you're looking at something curved, and this is actually what Calc 1 is all about, how do you talk about the slope of something curved? Well, this is the beginnings of it. You could just calculate the slope of a line through 2 points and say, well, that kind of gives me an idea of how steep the curve is in that general region. So keep this stuff in mind. I will use it in more specific examples later. But again, just remember that you want to start thinking about when we're relating two variables, having a direction. I'm plugging one of them in and I'm getting information out about the other one. And then memorize your domain range, try and get really comfortable with the f of x type notation. And we'll spend a few days on this section, so hopefully that won't give you too much trouble. And then we're going to move on to looking specifically at linear functions. So all that graph stuff you did in the last section will come back again in the following section, but we're going to use that function thinking and that function notation. Okay, thanks for watching.